motor performs.
The three factors that determine
the type of work a motor can produce
slowly
are speed, torque, and horsepower. The typical speed is defined as how fast the motor performs its work. For example, a shaft can rotate slowly or quickly. Is defined as a force.
The typical units of measurement for rotational motor speed are revolutions per minute or
RPM.
RPM.
Is called torque. Torque is a special type of work
is defined as a force applied over a distance. In the case of flywheels, winches, and motors,
on a radius.
the work is called torque.
Typical units
torque
of measurement
is a special type of work that produces rotation.
The torque
occurs when a force
acts
on a radius.
Pound-foot.
Typical units of measurement for torque
horsepower is defined
foot.
as the rate at which work is accomplished.
The torque
Years
illustrated
ago,
here
before motors
is
were
equal
invented,
to 1
most
pound-foot.
work was accomplished manually.
Horsepower is defined as the rate at which work is accomplished.
Approximately
years ago, before motors were invented, most work was accomplished
the
manually.
Horsepower was born.
It was estimated that one horse could accomplish approximately 33,000 pound-foot of work per minute,
and can be
and thus the
translated
term
into
horsepower
watts,
was born.
BTUs, joules, or any unit
In
of
modern
power.
terms,
Units
horsepower
that
is simply
motor power
another
are
unit of
typically
measurement
in
for power
or
and can be
watts.
translated into watts, BTUs,
You can manipulate the
joules,
connection
or
among
any
speed,
unit of power.
torque, and horsepower
Units that
by
measure motor
understanding
power
how
are
they
typically
related.
in
The
horsepower
work
or
accomplished
watts.
here, the torque, is represented by
You
the
can
weight
manipulate the
moving along
connection
the
among
conveyor.
speed, torque,
If
and
torque remains
horsepower by
constant,
understanding
speed
how
and
they are
horsepower
related.
are proportional.
The work accomplished
As the
here,
speed
the
or
torque,
RPM
is represented
increases,
by the weight
horsepower
moving along the
increases
conveyor.
to maintain constant
If torque remains constant, speed and horsepower are
If
proportional.
speed decreases,
As the speed or
horsepower
RPM
decreases to
increases,
maintain constant
horsepower
torque.
increases to maintain constant torque.
Let's say we wish to keep torque constant, but want
If
to
speed
increase
decreases,
the production of
horsepower
barrels.
decreases
If the torque
to maintain
or number of
constant
barrels
torque.
on the conveyor belt remains constant,
Let's
but
say
speed
we wish to keep
increases,
torque
then the
constant,
horsepower
but want to
of the
increase
motor
the production
also
of barrels.
increases.
If the torque or number of
In
barrels
other
on the
words, a
conveyor
more
belt
powerful
remains
motor is
constant,
required
but
to
speed
produce the
increases,
same amount of
then the
torque more
horsepower of the
quickly.
motor also increases.
Similarly, the opposite is true.
In
If
other
we
words,
wish torque
a
to
more
remain
powerful
constant
motor
and
is
decrease
required
speed,
to produce
then
the same
horsepower
amount
of
of
the
torque
motor
more quickly.
also decreases.
Similarly, the opposite is true. If we wish torque to remain
If
constant
speed
and
remains
decrease
constant,
speed,
then
the
torque
horsepower
and
of the
horsepower
motor
are proportional.
also decreases.
As the torque increases, horsepower also increases to maintain constant
If
speed.
speed remains constant, then
As
torque
the
and
torque
horsepower
decreases,
are proportional.
horsepower
As
also
the torque
decreases
increases,
to maintain
horsepower
constant
also
RPM.
increases to maintain constant speed.
Let's say we want production to increase,
As the torque
but the speed of the
decreases,
conveyor
horsepower
to remain
also
constant.
decreases to
If
maintain
torque
constant
increases,
RPM.
horsepower also increases to compensate.
Let's say we want production
This means
to
a more
increase,
powerful
but
motor
the
is
speed of the
needed to
conveyor
produce
to
more
remain
torque
constant.
at the same speed.
If torque increases, horsepower also
Similarly,
increases
the
to
opposite
compensate.
is true.
This means
If
a more
we wish
powerful
speed
motor is
to remain
needed to
constant
produce more
and
torque
decrease
at the same
torque,
speed.
then horsepower also decreases.
Similarly, the opposite is true. If we wish speed to
horsepower
remain
remains
constant and
then
decrease
speed
torque,
and torque
then
are
horsepower
inversely
also
proportional.
decreases.
As the torque increases, speed decreases to maintain
If
constant
horsepower remains constant,
As
then
torque
speed
decreases,
and torque
speed
are
must
inversely
increase
proportional.
to maintain
As
constant
the torque
horsepower.
increases, speed decreases
Let's
to
say
maintain
we want
constant
the horsepower
horsepower
of our motor
As
to remain
torque
constant,
decreases,
but wish
speed
to
must
increase
increase
the torque.
to maintain constant horsepower.
If torque increases, the
Let's
speed
say
of the
we
conveyor
want the horsepower
decreases,
of our
so
motor
that the
to remain
horsepower
constant,
required of
but
the
wish
motor
to
remains
increase
constant.
the torque.
Similarly, the opposite is
If
true.
torque increases, the speed of the
If the
conveyor
torque
decreases,
decreases, the
so that
speed
the
of the
horsepower
conveyor
required
increases,
of the motor
and the
remains
horsepower
constant.
generated by the motor
Similarly,
remains
the opposite
constant.
is true. If the torque decreases,
To
the speed
calculate
of the
amount of
conveyor
horsepower
increases,
required to
and
move
the
a
horsepower
horizontal
generated
load,
by
we
the
must first
motor
consider the
remains
occurrence
constant.
of sliding friction. Friction occurs when two
To
materials
calculate the
resist
amount of
moving
horsepower
against one
required
another.
to move a
For
horizontal
example,
load,
it's much
we must
easier to
first
pull a
consider
block
the
of metal
occurrence of
across a
sliding
smooth
friction.
field of ice than it is to pull it
Friction
across
occurs
a rocky
when two
path.
materials
The
resist
friction
moving
between the
against
block
one
and the
another.
rocks is greater
For
than the
example, it's
friction
much easier
between
to pull a
metal
block
and
of
ice.
metal across a smooth field
The
of
amount of
ice
friction
than it
generated
is to pull it
depends
across a
primarily on the
rocky path.
materials which are
The friction
in sliding
between the
contact.
block and the rocks
The
is greater
coefficient
than the
of
friction between
symbolized
metal
by the
and
Greek
ice.
letter mu is
The
a
amount of
dimensionless
friction
quantity
generated
which
depends
describes the
primarily
ratio
on the
of
materials
force of
which
the
are
friction
in sliding
between
contact.
two bodies
The
and the force
coefficient
of
of
them
friction,
pressing
symbolized
together.
by the Greek
This
letter mu,
coefficient can be
is a
used to help
dimensionless
determine the
quantity
amount of
which
force
describes the
required
ratio
to
of the
move a
force
load
of the friction
horizontally across
between
a
two
surface.
bodies and the force of them
Many
pressing
manufacturing
together.
handbooks contain
This
tables that
coefficient
publish
can be
the
used to help
coefficient of
determine the
friction
amount
for
of force
common
required
materials.
to move a load horizontally
The
across
amount
a
of
surface.
force required to slide a load
Many
and
manufacturing
overcome the
handbooks
surface
contain
friction
tables
is
that publish
calculated
the
by multiplying
coefficient
the
of friction
coefficient
for
of
common
friction
materials
by the weight of the load.
The amount of force required to slide a load and
Once this
overcome the
force is
surface
determined,
friction
it's
is
easy to
calculated by
calculate the
multiplying the
required horsepower
coefficient
to
of
move a
friction
horizontal
by the
load.
weight of the load.
First, find the horizontal force required by multiplying
Once this
the
force is
coefficient of
determined,
friction
it's
by
easy
the
to
weight.
calculate the required horsepower
Then
to
determine
move
the
a
amount
horizontal
of work
load.
required by multiplying
First,
the force
find the
by the
horizontal
distance
force
in feet to
required
be
by
moved.
multiplying the coefficient
Next,
of friction by
calculate
the weight.
power by dividing the
Then
work
determine
by
the amount of
in
work
minutes.
required by multiplying the force by the distance
Then
in feet
convert
to be
to
moved.
horsepower by dividing the result
Next,
by
calculate the power by
33,000.
dividing the work by the time
Finally,
in
add
minutes.
5% to compensate for estimated friction losses in
Then
the motor
convert
or
to
cylinder.
horsepower by dividing the result
Let's
by
try an example.
33,000.
Assume the barrel weighs 100
Finally,
pounds.
add
The
5% to
coefficient of
compensate
friction
for
between the
estimated
belt and the
friction losses
platform
in the
is
motor or cylinder.
0.3, and the barrels move
Let's try
20
an
feet
example.
in 0.1
Assume the
minutes.
barrel weighs
We
100
can determine
pounds.
the horsepower
The coefficient
required
of friction
the
between the
conveyor
belt
motor
and
by
the platform
accomplishing the
is
following
0.3,
calculations.
and the barrels move
First,
20
find the
feet in
horizontal force
0.1
required by
minutes.
multiplying the
We can determine the
coefficient of friction
horsepower
by the
required
force
of the
of
conveyor
weight,
motor
which is
by
100
accomplishing
pounds.
the following
In this
calculations.
system, the horizontal force
First,
is
find
30
the horizontal
pounds.
force required by
Then
multiplying the
determine the amount of
coefficient
work
of friction
required
by the force
multiplying
of the
the
weight,
force
which
by
is
the
100
distance,
pounds.
20 feet.
In this system,
For this
the
system,
horizontal
the work
force
required
is
30
600
pounds.
foot-pounds. Then determine
Next,
the amount of
calculate
work
the power
required by
taking
multiplying
work
the
and dividing
force
by
by
the
the
time,
distance, 20 feet.
0.1 minutes.
For this system, the
power
work
is equal to
required is
6,000
600 foot-pounds
per minute.
Next,
Then
calculate
convert
the
to
power by
horsepower
taking
by
the work
dividing the
and
result
dividing by
by
the time,
33,000.
0.1
This
minutes.
yields a result
the power
of
is equal to
0.18
6,000
horsepower.
foot-pounds per minute.
Finally, add 5%
Then convert to
compensate
horsepower
for
by
estimated
dividing the
friction
result
losses
by
in the motor or
33,000.
cylinder.
This
The
yields a
final
result of
is
0.18 horsepower.
With this
Finally,
result,
add
system
5%
designers
to
can ensure
compensate
the
for
right
estimated
size motor
friction
is
losses
available
in the motor
to
or
operate
cylinder.
the conveyor.
The final result is 0.19
If the distance to be traveled
horsepower.
isn't on a
With this
horizontal
result,
surface,
system
the angle of
designers
the
can
surface
ensure the
must be
right
taken
size
into
motor
account.
is available to operate
To
the
determine
conveyor.
the total force required, we must add
If the distance to be traveled isn't on a horizontal surface,
elevation,
the angle of the surface must be taken into account.
the friction.
To determine the total force required, we must add the force required to raise the load to a higher elevation with the force required to overcome the friction. The total force is equal to the weight times
Once
sine
these two
A
forces are
plus the
combined,
weight
we can
times the
continue with the
coefficient
same
of
steps
friction
used
times
previously
cosine
to calculate
A.
the size of the motor required. First, find the horizontal force
Once
required
these two forces
by
are
adding the
combined,
force
we can
required to
continue
raise
with the
load
same
to a
steps
higher
used
elevation
previously to
with
calculate the
force
size
required
of the
to
motor
overcome the
required.
friction. In this system,
First,
the
find the horizontal force
is
required by adding the
75.98
force
pounds.
required to raise the load to a
Then
higher
determine
elevation
the amount of work
with the force
required by
required to
multiplying the
overcome
force
the
by the
friction.
distance,
In
20
this
feet.
system, the horizontal
For this
force
system,
is
the work required is
75.98 pounds.
1,519.6
Then determine the amount of work required by
Next,
multiplying the
calculate
force
power
by the
taking
distance,
the work
20
and
feet.
dividing by the
For
time,
this system, the work
0.1
required
minutes.
is
The power is equal to
1,519.6
15,196
foot-pounds.
per
Next,
minute.
calculate the power by
Then
taking the
convert
work
to
and dividing by the
horsepower by
time,
dividing the result by
0.1 minutes.
33,000.
The power
This
is
yields
equal
a result
to
of
15,196
0.46
foot-pounds per minute.
Finally, add 5%
Then
to
convert
compensate
to
for estimated
horsepower by
friction
dividing the
losses in
result
the
by
motor or cylinder.
33,000.
The
This
final
yields a result
is
of 0.46
horsepower.
horsepower.
With this
Finally,
result,
add
system
5%
designers
to
can ensure
compensate
the
for
right
estimated
size motor
friction
is
losses
available
in
to
the motor
operate
or
the
cylinder.
conveyor on an incline.
The final result
As
is
expected, it takes a
0.48
stronger
horsepower.
motor to move weight up an
With
incline
this result,
than on a
system
horizontal
designers can
surface.
ensure the right size motor is available to operate the conveyor
relationships
on an
among
incline.
horsepower,
As
speed,
expected, it takes a
RPM,
stronger motor
work,
to move weight
power,
up an
and
incline
force
than on a
allow
horizontal
technicians
surface.
and system designers to determine the appropriate
The
characteristics
relationships
of
among
motors,
horsepower,
cylinders,
speed,
and other fluid system
RPM,
components
work, power,
required to
and
operate
force
any
allow
system.
technicians and system designers to determine the appropriate characteristics